To distinguish spin angular momentum from orbital angular momentum, we will use the quantum numbers s rather than L, and sigma, that's the Greek letter sigma, rather than m. To reconcile this with the quantum mechanics of angular momentum, to get 2s plus 1 equal to 2, we would need to have s is equal to a half. And that's very different from what we did with L, because L could only take on integer values. But here, to get two possible levels in our Zeeman experiments or our Stern-Gerlach experiments, we would have to assign this s to be a half by analogy with what L is for orbital angular momentum. Hence, we assign total spin angular momentum of h bar s equal to h bar over 2 to the electron. We say that sigma, which is the analog, you remember, of m, can take values in integer steps from minus s to plus s, just like m could take values in integer steps from minus L to plus L. And so sigma, therefore, is minus a half or plus a half. And the corresponding z angular momentum component, that is in the z direction, is sigma h bar. From our previous understanding of angular momentum, this value of 1/2 is bizarre. Angular momentum associated with wave functions has to have an integer for the m quantum number, otherwise the spatial wave function would not be single valued after a complete rotation about the z-axis. How then can we have the sigma quantum number be a half integer? The answer to which we are forced is that the eigenfunctions associated with this internal spin angular momentum of the electron are not functions in space. We cannot describe the behavior of an electron, including its spin, only in terms of one function amplitude in space. For a complete description, we need another degree of freedom, the electron spin. Incidentally, and somewhat confusingly, the spin magnetic moment of the electron is not actually just sigma times the Bohr magneton. The orbital angular momentum spin magnetic moment was just m times mu b, but for the electron, actually we get another factor in here, g, called the gyromagnetic factor, and it's not even an integer. There is now no radius of classical orbit of an electron that will give it both an angular momentum of h bar over 2 and a magnetic moment of plus or minus g times the Bohr magneton over 2. So that further confirms for us that spin really cannot be considered as corresponding to a classical orbit of any kind. Suppose for the moment that we are only interested in the spin properties of the electron. Let us go back and consider how we would have described an angular momentum state in the orbital angular momentum case without describing it explicitly as a function of angle in space. Suppose, for example, that we considered only states with a specific value of L in ordinary orbital angular momentum. And we could write that as a ket vector. We could put L inside the ket vector as a label. In general, such a state would be some linear combination of the basis states Lm, basically the spherical harmonics here, corresponding to any of the specific allowed values of m. So a general orbital angular momentum state with quantum number L could be any linear combination of this set of states, all of which have got quantum number L, but we could have different amplitudes of the ones corresponding to different m's. So that's just a general linear combination of all the states with the same L. In the case of these states, then, each of the states could also be written as one of the spherical harmonic functions in space. And the resulting linear combination can therefore also be written as a function of angle in space. We could also, if we wish, write this general state here out explicitly as a vector just of these values here. So all the way from AL to A minus L down here, with M as the index. Note that the set of functions corresponding to all the possible values of M for a given L is a complete set for describing any possible function with that value of L, including even the eigenfunctions of Lx and Ly, which are actually oriented round the other axes. In the case of the electron spin, we cannot write the basis functions as functions of angle in space. That doesn't work. But we do expect that we can write them using the same kind of state and vector formalism as we use for other angular momenta. For electron spin, that formalism becomes very simple. Instead of L, we have S, which we know is 1/2, and instead of M, we have sigma. There are, however, now only two basis states. So this would be S equal to 1/2, sigma equal to 1/2, and S equal to 1/2, sigma equal to minus 1/2. This is analogous to solutions of the spherical harmonic problem with L and M values. But we only have two basis states here. And these correspond, as I said, to sigma equal to 1/2 or sigma equal to minus 1/2. Hence, writing our general spin state, S, we have a linear combination of this state with sigma equal to 1/2 and this state, sigma equal to minus 1/2. And these are our presumed coefficients here. We can also write that in this form, it's just a notation here, or we can write it in a simple vector form. And here we have introduced this idea of this representing what we'll call spin up, it's just a shorthand for that state, and this representing spin down, it's just a shorthand for that state. The up and down conventionally refer to the z direction here. Any possible spin state of the electron can presumably be described this way. Rather obviously, a state with its magnetic moment in the plus z direction would be the spin up state, and that we could write as 1,0 in our simple vector format. And a state with its magnetic moment in the minus z direction, the spin down state, could be written in this vector form. The choice of unit amplitudes for these states also assures that they're normalized. Normalization here means assuring that the sum of the modulus squared of the two vector elements is equal to 1. So formally, the amplitude of the spin up state, modulus squared, plus the amplitude of the spin down state, modulus squared, should add to 1. As usual, we could also multiply these states by any unit complex number, and they would still be versions of spin up and spin down states, respectively. We might think that these vectors, 1,0 for spin up and 0,1 for spin down, can represent only spin up and spin down states, oriented along the z-axis. In fact, these two basis vectors can represent any possible spin state of the electron, including spin states with the magnetic moment oriented along the x direction or even oriented along the y direction. We can understand how this works once we define the spin operators. At the moment, it may seem very strange that we could write left or right as a linear combination of up and down, but that's because we're not looking at this correctly from a geometrical point of view.